Right, this is a problem from CSIR NET 2023. Um, part it's part C. It says that let G1 and G2 be two groups, and phi a mapping from G1 to G2 be an onto group homomorphism. It is given that this mapping is an onto group homomorphism. We are interested which of the following are true. The first part is if G is cyclic, then so is G2. When we talk about solution of this, okay, given G1 is cyclic, so G1 there exists an element of which it is can be written as a cyclic, let's say A. To show G2 is cyclic, okay, let alpha belongs to G2 be any arbitrary element, then alpha is equal to some phi B for some B belongs to G1 because phi is on 2. This is possible because phi is on 2. Okay, now as B belongs to G1 and G1 is a cyclic group, so we can write B as something a to the power n, or some n belongs to natural number. Thus, alpha can be written as phi a to the power n, which will be equal to phi a to the power n. Thus, alpha is phi a to the power n. Alpha was an arbitrary element of G2, and we can write it as a power of phi to the power n. Thus, we claim that G2 is a cyclic group generated by phi A, image of phi A, and where A is the cyclic group, A is the element which generates the cyclic group G1. So, first is true. Now we move on to second. In second, we are interested if given G1 is abelian, G2 is abelian or not. Okay, let alpha beta belongs to G2, arbitrary element. To show it is abelian, we need to show these elements commute. Okay, since phi is onto homomorphism, alpha is equal to some phi A, where A belongs to G1, beta is equal to phi B, B belongs to, so some B belongs to G1 again. Okay, so now phi A alpha dot beta is equal to phi A dot phi B, which is equal to phi A dot B from the property of group homomorphism, which is equal to phi B dot A as G1 is abelian given. Phi B dot A, which is equal to phi B dot phi A, which is again as property of the group homomorphism, and this is equal to beta dot alpha. So we have proved that alpha dot beta is equal to beta dot alpha, therefore commute. Therefore G2 is abelian. Hence the second part is also true. Second is also true. Now we will see about third part. Third is asking if H is a subgroup. So is phi H. Okay, to show phi H is a subgroup, We need to show that it has identity, and second, close under operation. Inverse exists for every element. The inverse exists. This is the three things we need to show. There are some that properties too of two step. You can use that too, whatever suits. First of all, more interesting is that if E identity in H, then phi E is identity in E is identity in G1. E is identity in G1, then phi is identity in G2. Simply we take any alpha belongs to G2, then alpha is equal to phi A. Okay, because phi is on 2. Now alpha dot phi E is equal to alpha phi A dot phi E, which is equal to phi A dot E is equal to phi A, which is equal to alpha. Similarly, we can from right hand side to phi E dot. Okay, similarly, we can show from right hand side to that E phi E dot alpha is equal to alpha. So what we have shown that phi E is identity in G2. Okay. Okay. So now as we are given that H is a subgroup, E is the identity in G1, then phi is identity in G2. We have shown up till now, and now okay. So as H is a subgroup, H is a subgroup of G1, so H has identity, and so is phi E belongs to phi H. Thus phi H contains identity. So we have shown that phi H contains identity. Identity which is phi E. Okay. Now given to show that it is closed under product. Let alpha comma beta belongs to phi H. Then again alpha is equal to some phi H1, and beta is equal to some phi H2. H1 comma H2 belongs to H. Now alpha dot beta is equal to phi H1 dot phi H2, which is by the property of the group homomorphism is equal to phi H1 dot H2. Now H1 dot H2 belongs to H, as H is a subgroup. Thus this product belongs to phi H. H1 as, I will write it down as H1 dot H2 belongs to H. This implies phi H1 dot H2, which is equal to alpha dot beta, belongs to phi H. Thus we have shown that it is closed under product 2. Now to find the inverse, simply if alpha belongs to phi H, then again alpha is equal to some phi A belongs to H. This implies if A belongs to H, then A inverse also belongs to H, as A is a subgroup. A inverse belongs to H, then phi A inverse belongs to phi H. Now we take the product phi A dot phi A inverse, which will be equal to phi A dot inverse, which is equal to phi E, and this is the identity of G2. And similarly from other side to phi A dot phi A is equal to phi A inverse dot A, which is equal to phi E. This is identity of G2. Thus phi A inverse is equal to inverse of phi A whole, which is equal to alpha inverse. So for any alpha belongs to phi H, we have find is inverse, alpha inverse, which belongs to phi H. Thus phi H is a subgroup. Now we come to the last part, which says that if this is fourth part, if n is normal in G1, then so is phi n in G2. Okay, so how to show some subgroup normal? We need to show that phi n into alpha inverse is a subset of phi n. This is we need to show for all alpha belongs to G2. This is how we show a group is a normal subgroup. Okay, take any element of this phi a, let's say phi a alpha inverse is equal to phi a dot phi, let's say it's n, for any n. Alpha phi n, for any n belongs to n, first of all see that phi n belongs to phi n, there's no doubt. Now consider alpha dot phi alpha inverse, which is equal to phi a into phi n into phi a inverse, as alpha belongs to G2 and phi is an onto map, so there exists and A belongs to G1. Okay, this all is possible because phi is onto. Thus alpha phi n alpha inverse is equal to phi a dot n dot A inverse. From here this is the next step. And where does this belongs to? A belongs to G1, n belongs to n. N is normal. N is normal, thus A inverse belongs to n. This, this implies phi A inverse belongs to phi n. Hence, alpha phi n alpha inverse belongs to phi n. As alpha was arbitrary element of G2, thus this implies that phi n is a normal subgroup. G2. Okay, so now we get back to the original question. So we have seen that third is true, fourth is true, all the options are correct.